I wanted you, because there will be a quiz, you need to know the difference between dark matter. I apologize, this slide didn't project very well. The difference between dark matter and dark energy. So dark energy has dark matter has attractive gravity. It's what holds our galaxy together. Dark energy has the repulsive gravity. And it determines its destiny. I have to show you this very quickly. What is our evidence for exotic dark matter? So this is one of the numbers we're really proud of. We measure the amount of ordinary matter, which is this line, from the amount of deuterium made in the Big Bang and from the microwave background, and we get this number. Don't worry, it's 0.02. It's not quite what you've seen earlier, with a very tiny error mark. We measure the total amount of matter in the universe largely by the height of this first peak and by the large-scale structure of the universe, and we get this number, 0.13, with that error bar. Those two numbers don't agree. How big is the discrepancy? It's 20 standard deviations. How many people know a little bit about statistics? Okay. It's worse than one of the parties saying that the polling numbers are way off. Here's how much matter there is on a ruler, and this is the range, how big it could range, and that's how many atoms there are, and that's the space in between. So this is really exciting. We put ourselves out on a limb. We said most of the matter in the universe is a new form of matter. That's the most conservative hypothesis. It may not be right, but right now that's the corner we worked ourselves into. Oh, I know you all want to know this. So, because I know you all learned on your mother's knee about the 3 Big Bangs, right? There you're on your mother's knee, you're falling asleep, she's saying the 3 kind of Big Bangs, droopy lines, blah, blah, blah. Was your mother wrong? Mothers are never wrong. As you were falling asleep, your mother said, of course, that's a simplified story. If we had dark energy, then the universe can accelerate. And so we are this universe. We are the Goldilocks flat universe, but we are accelerating, so the curve is not droopy, it's moving upward. And what I wanted to show here is, until we understand what the dark energy is, we can't predict the fate. And remember, in Sandage's simple universe, the geometry and the fate were connected. We've now measured the geometry, but we don't know the fate. Isn't science wonderful? You ask one question, you get an answer, and you get a couple new ones. So if the dark energy is vacuum energy, the universe will continue to accelerate. In 100 billion years, we won't be able to see any other galaxies except Virgo, and we won't be able to do astronomy. So this is a very powerful argument for increasing funding in astronomy. It could be that the dark energy, in fact, Alan Greenspan has a theory of this, that dark energy is just kind of a mild period of inflation that will pass. Well, he's been right on so many things. It could still be that we recollapse, or there's even something called the Big Rip, which you can ask me about. Quarks to the cosmos. So the deep connection is not this. This was just to get your interest. The deep connection between between quarks and the cosmos is the dark matter, is the inflation that the largest things in the universe started as quantum fluctuations, and the dark energy. And then finally, just to bring you up to next time, I show you this. This is a wonderful story. I've convinced you that we have this marvelous understanding of the universe. And before somebody asks a question, you know, in politics, if you've got bad news, you get it out yourself, you don't let your... So before anybody can say this, so we have this beautiful model, you know, inflation, quark soup, Big Bang nucleosynthesis, but it seems to rest on 3 pillars: dark matter, dark energy, and inflation. And if you listen really carefully, or if you ask one of your particle physicist friends, none of those things are actually known to exist. Yet. And so you might say, gosh, aren't you kind of doing Ptolemy all over again? You know, you make these measurements, you can't really understand them, and you invent little epicycles, and so that's what we'll take up next time. I view this very, very differently. I view this that we have discovered a new form of matter, and now we have to go out and identify that. That happened once before. Helium was discovered by looking at the sun, and then it was found on Earth. This dark energy, that's a big, big mystery. And inflation is a new scalar field, and so we have to go out and figure out these mysteries. That's, ooh, I didn't mean to say that, but I believe that. Thank you very much.